Hi everyone, welcome back. In this video I will share with you how to implement PID in step 7 using the SFB41 block. We will also test it by designing a Lovely HMI interface in TIA Portal. Let's get started. Kindly subscribe if you've not done that already, and also press on the notification bell. This way you'll always be notified whenever I upload new videos. PID is an acronym that stands for Proportional, Integral, and Derivative Control. It can basically exist as a physical standalone unit or a function block in a PLC controller, such as the Siemens, Allen Bradley, etc. The PID section of the modern controllers is a series of numbers that are used as adjustments in order to achieve process objectives. Now let's look at an example of trying to keep our home storeroom temperature at a set value. This storeroom has an extractor fan that extracts heat from the room and a wall mount controller called the thermostat. The thermostat has a sensor that measures the storeroom temperature, which is known as the PV, and compares it to an adjustable set point, also known as the SP. If the storeroom temperature is above the set point, the fan turns on, and if it falls below the set point, the fan turns off. This type of control is called on-off control or bank-bank control. This is a graph of how the room temperature will look like whilst the fan switches on and off over a period of time. As you can see, the temperature keeps fluctuating around the set point and will never be equal to the set point. This type of control may be okay for your house. However, this is not good for most industrial process, hence the need of a PID control unit. PID controller basically determines how much and how fast correction is applied. By using proportional, integral, and derivative action, each parameter contributes a unique signal which are added together to create a controller output signal called the MV, which is the manipulator variable, CV, control variable, or what we term as the final control element. This is a feedback control loop which needs to keep a set point at the process. And to do this, a process variable is transmitted, and this variable is compared to the set point. The difference between the set point and the process variable is what we term as the error. This error is fed into the PID. The PID calculates and then gives a suitable output which regulates the final control element to keep the process stable. Now let's talk about what each of the PI and D components of the PID function is. From the previous diagram, we know that the error equals the set point minus the process variable. The proportional block creates an output signal proportional to the magnitude of the error signal. Unfortunately, with the proportional action, the closer you get to the set point, the less it pushes. Eventually, the process just runs continuously close to the set point but will never get to the set point. Hence, the need for the integral action. The integral block creates an output proportional to the duration and magnitude of the error signal. The longer the error and greater the amount, the larger the integral output. As long as an error exists, integral action will continue. The derivative block creates an output signal proportional to the rate of change of the error signal. The faster the error changes, the larger the derivative outputs. Controller tuning is the act of correctly setting the controller PI and D values for specific process requirements. There are many manual methods of controller tuning. One is by increasing the amount of set points change and repeating the procedure until the process enters a state of steady state oscillation. This method produces good results, however, not practical in many applications. Most process controllers, PLCs, and DCS that are sold currently have what we term as the auto-tuning capability. In auto-tuning mode, the PID controller learns how the process responds to a change in set point and suggests appropriate PI and D settings, regardless of whether the initial PID parameters are derived from a manual or auto-tuning method. Additional tweaking is mostly required and are done by seasoned automation professionals to get the response desired. With this PID basic understanding, let's move on, implement and simulate our PID example in step 7. Okay, we move to File and then we select New. We now give it a name, PID underscore test underscore sim. We now move on and add a station. We go to Insert and then we click on Station and then we add 300 station. We now drop this and then move into the hardware and then configure our hardware. We drop the schematic 300, we insert a rail, readjust the rail. We now move on and add a CPU. We drop the CPU and then select a CPU which can handle Profinet and then Profibus as well. This is the IP of the CPU. We now need to create a network. We click on New and then click on OK. OK again. Network is created. We readjust and now compile. We now move on, click on block. We already have our OB1 created. We send it to functional block diagram and now we create our PID function. So we go to function and then create FC1, and this is our PID for CMO1. We give it a description, PID test, and then click OK. Okay, we open it. We now move on to our standard library and we have various PIDs. We now select the continuous type, which is the first item. If you want the help manual, you click on it and this will give you a description of how this block functions. Pretty straightforward. We now drag our SFB 41 onto our first network and then give it a description, PID. We then need to give it an instant DB. It is now created. We double click on it. Okay, we can now give it a property. So we give it the same name, CMO1 underscore PID underscore tests, and it's our DB. Now it's created. We now go back to our FC and we can see that we have our DB created now. There are various parameters on this block and the description of each parameter can be found in the manual. This is the input side. These are the descriptions and this is the output side and these are the descriptions. We will move on. Now the input of our interest is the manual, so I'll put a memory there, 0.0, so we can switch our PID to either auto or manual. We give it a symbolic name and a description, or let's say a comment. Okay, the next item of interest is our manipulated variable, which is our LMN. So we give our manipulated variable, so it's db1.lmn and then we go back to the PV. In this simulation, the manipulated variable is what we will fed back to as our process variable. We will now create a new network because our set point we need to do a conversion. So I will switch to statement list, and then I'll say load memory word 4, and then integer to double, then double to real, and then transfer it to the DB, that is the PID DB, which is DBD6. I switch back to functional block, and now I'll open the DB of the PID, and then we can see the structure. Okay, great. We can see where our set point is located. It's at 6, and that's what I've specified here. I'll copy this, and then I can paste it at the set point in position. So we have the set point. I paste it there, and I'll click on save, and I'll open the simulator, and this is our memory word byte 0, and then memory word 4 or set. I will now download the program into our simulator. Click yes throughout, and now I'll move on and insert OB35. Remember, PIDs are supposed to be called in interrupt OBs, and one OB is OB35. So I call OB35, double click on it, and then I can now call my FC1 here. So I give it a description, switch to statementless, and I say call FC1. You can use this approach to call the FC, or you can drag it from here onto your network if you switch to either ladder or functional block. Okay, I switch back to functional block, and we can see our block is called. I click on save, and then I click on download. Great. I now switch to our FC, and then click on save, and then download here too as well. And I go online. My PLC is in stop mode. I switch to run mode, and then we can see that our block is online now. I now switch to manual mode, and we can see that it's active on the block. I go offline and now switch to TI Portal to create our HMI interface. I now create a project, CMO1_PID_test. I click on create, and I click on project view, and now go to add device. I select HMI, and then click on the 9 inches, and then use the TP900 comfort. For this example, I click on OK. You click on next, 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 next again, and then click on finish. We now do our connection. Double click on the connection, and this will establish connection between the TI Portal simulator and then the step 7 simulator. So this is what we have, 300/400. Switch this one to Ethernet, and then we can see the IP address of the HMI as 2 and the IP address of the simulator as 1, and we can see is the same address located here. I click on save. We now add HMI tags. I double click on HMI tag, click on add new tag, click on this section, and then click on new. Our first item is LMN, which is real. Second item is our PV process value, which is real, and then our set point, which is an integer. We will now do our connection settings. I select the connection, the next one connection, and do for all. Great. We now need to set our addresses. The first one is 72, second is 10, and then the last one is a memory word. So I have to delete and create memory word 4. Great. With this done, we will now go back to our screen and now create our HMI design. I need something to indicate a process variable, so I'll use this graph. And then I need something to set the set point, so I'll use this slider. And then we need to display the waveform, so we'll use this chart. Okay, great. We now need to configure them. We go to Property, General, and we can see that we have the minimum 0, max 100. And now go to the process tag and assign the set point to this. And now move on. We can see all that. And now move on and assign the process variable. Go to process tag, select the process variable, click on the correct sign, and we can see that one has also been assigned. Okay, great. And now move on to the chart. Select the first item, that is the trend 1. I will need 999 to get a bigger scale. And now assign the tag to it. And this is our set point. It's assigned. And now move, click on the new, add the next item, our process variable, and it's assigned. Move to the final one, which is the manipulated variable, and then click on the correct to assign it. Great. And now click save and then compile. We can see compilation is done, no errors. And now select this item and then click on the simulator, or what we term as the runtime. Great, we have the interface opened. And then when I slide the bar, I can see that we have our set point, but the process and the manipulated variable are all shown in 0, which indicates that our PID is in manual mode. I go online on the DB and we can see that our PID is in manual mode, so I switch it into auto mode. And then we can see that we are having erratic reading on the process variable because it's not well tuned. So I set the gain to 0.06, the time to 10, and then the next one to 7, and then 1. Download. And we can see that this time the PID is acting correctly and is trying to force to achieve the set point. And it's going gradually. We can see that it's a bit sluggish. So we need to try and tune it well again. So let's see. You can see it's taking quite some time to reach the set point. So I change this value to 0.5. And then I change the integral time to 5, and I change the derivative time to 4. And then I click on the download again, and then I change the set point to see the action. We can see that now it's achieving the set point a bit faster. Great, it's working perfectly well. I push the set point up again, and we can see how fast it's able to achieve the set point, working perfectly well. I now try and change the set point from the simulator. That's the step 7 simulator, and we can see it's also working perfectly. Great. Viewers, this is how we implement PID in step 7 and then use HMI interface from TI Portal. Thank you all for watching. See you in the next tutorial. Bye bye.